Hi everyone, my name is Catherine, and today my co-author Martine and I are going to be talking about our work in learning sampling distributions for efficient planning in hybrid geometric and object level representations. This is joint work with Nick Roy at the Robust Robotics Group at MIT. In this work, we would like to enable a robotic agent to quickly and intelligently find promising trajectories through structured unknown environments. This ability will be crucial to deploying robots in a wide variety of tasks such as autonomous delivery and search and rescue, and is something you and I do on a regular basis. For example, if you were standing at the green circle in this building and I told you that your goal was outside somewhere, you would probably pick up on the partially visible exit sign and choose to follow the green path over the blue path down the hallway. On the other hand, if you were again at the green circle and I told you the goal was outdoors and far to the left, you'd probably naturally follow the road as the green arrow does instead of trying to go through an apartment like the blue one. In contrast to the object-centered navigation strategies I just described, most robots in practice use representations such as this 2D occupancy map to pick trajectories. Instead of capturing explicit semantic information, occupancy maps encode in geometric detail which parts of the environment are untraversable. It is straightforward to find trajectories that are not in collision with the environment with maps like this. For example, in this fully known map, it's relatively easy to find the shortest path that will take us from the start to the goal. However, it is often infeasible to have maps a priori, and with range and field of view limited sensors, there will be parts of the environment the robot has not mapped yet. A common assumption is to optimistically treat this unknown space as unoccupied, but this assumption can lead to the myopic navigation behavior shown here, where the simulated robot explores unnecessary rooms. In more extreme cases, a robot might not even be able to find a plan in its allotted computation budget if it considers all unknown space as being useful to find a plan.
To unpack why navigating on partially observed geometric representations is inefficient, let's consider this underlying true map. At the current time step, our simulated robot has only uncovered this portion of the map. Let's consider again trying to navigate from the green circle to the red circle with the available information. In this case, the blue trajectory appears to be low cost and feasible because it does not intersect with the white occupied space. But just a few slides ago, we showed how rich object-level semantic information from an image can be. Let's imagine for a moment that this image was taken from onboard the robot. It would be immediately clear that instead of turning around, the robot should go straight through the door. By combining low-cost object detection with object-level SLAM, we can even explicitly detect doors and other objects, and build a persistent map of objects similar to the one shown here that is keeping track of both the door and a window no longer fully in view of the hypothetical camera. However, this object-level information is not as straightforward to incorporate into planning as dense geometric information. We still need to capture how agents should interact with object-level information, in the same way that we decided free cells and occupancy maps indicate valid traversals, while occupied cells indicate collision. For instance, in our running example, we would like for the agent to go through the door. But is go through doors a sufficient navigation rule? We argue no. If the goal was behind the robot, the room structure in the occupancy map indicates that turning around is the best option. But now if we are told that the goal is outdoors and there's an exit sign next to the door, suddenly going through the door becomes a more promising navigation strategy. These examples illustrate that there are complex interactions between objects, dense geometry, and the objective of the agent. And while this richness is exactly what we set out to model, it is also what makes this problem challenging. An agent must quickly identify and choose between complex navigation behaviors when planning. We know we want to use semantic information to inform navigation, but it's not clear how to define all possible agent-object interactions. So the question that we are faced with in this work is, how can we model the complex relationship between geometry and semantics to determine where good plans lie?
A key insight in our work is that probability distributions are a natural way to capture this richness. The framework of sampling-based motion planning gives us a way to utilize a sampling distribution learned from experience to focus our planning efforts on promising navigation strategies. And in fact, the sampling-based motion planning community has shown that sampling-based motion planners can use informed sampling distributions to improve planning speed and performance. However, these works largely focus on safety and replanning speed in known environments instead of intelligent planning using partial information. Fortunately, we also have ample evidence from the planning under uncertainty community that we can learn useful properties about unknown space. We aim to combine the ideas from the sampling-based motion planning and navigation under uncertainty communities to learn the utility of potentially unknown parts of the environment using sampling distributions. Specifically, we encode useful navigation behaviors in a sampling distribution which is informed by partially observed geometric and object-level maps. This framework lets us use sampling-based motion planning approaches more effectively in novel environments.
So now that we've motivated learning a sampling distribution, how can we actually do this? It's not clear how to write down what the optimal sampling strategy should be given these incomplete maps. In this work, we will learn sampling distributions from previous experiences. If we only consider this partial occupancy map, the blue path appears to be the shortest path to the goal. However, if we have access to a ground truth map at train time, it becomes clear that the blue trajectory is not the right route to take. Using the known map, which we'll either obtain in the future or through simulation, which is how we do it in this work, we can calculate the true optimal trajectory, which is sketched here in green. And while we're at it, we can also get a label for what the optimal trajectory would be given a different goal, like the one shown here, which is to the right of the local map. Repeating this procedure, we can obtain many optimal trajectories for many different goals. This lets us generate a dataset that pairs incomplete object-level and dense geometric maps with true optimal plans given different goals. And even in the simple example, a clear pattern exists. Many of the trajectories pass through the door area, shown in yellow on the object-level map, so the door region is probably useful for navigation. There are also these trajectories that are long and relatively straight, which we can use to guess the presence of a hallway, shown in blue in the partial geometric map. Our goal is to learn these patterns from data.
With the dataset Martina described, we can train our network to optimize the likelihood of trajectories, with some simplifying assumptions on the probability of the trajectory. At train time, we pass our maps and some contextual information about the goal to our learned model to predict a sampling distribution P. We then score how likely it was that the true optimal trajectory would have been sampled under P, under some independence assumptions that are described in more detail in the paper. And that loss function backpropagates to the network. At runtime, we extract local body-centered maps and do a feed-forward pass with the network to obtain a local sampling distribution and assign a uniform density outside the local map. We sample points and build a graph. It's easy to see that in the limit of infinite samples and a Euclidean search metric, the path returned would still be the naive path. So we also propose using the probability distribution to bias the graph search to more likely trajectories, such as the one in green shown here.
We build our data set in simulation over 10 MIT floor plans and, after training our network, simulate in-the-loop planning with a PRM and our learned distribution. On the left, we show the simulated building of the semantic map. On the right, we show the learned distribution overlaid on the partial occupancy map. Our approach guides the simulated robot down the hallway and out the building to the goal. We compare our approach to a PRM using a uniform sampling strategy. In this example, the baseline optimistically enters 2 rooms in search of the goal. Comparing the trajectories, we see that the agent using our proposed strategy travels less distance overall. To evaluate the performance of our approach, we ran over 3,600 total trials by randomly selecting starts and goals over 3 novel maps not presented in the training data for different test conditions. If at any point during the course of a trial, one of the planners failed to find a plan, we marked that entire trial as a failure.
We find that our approach is up to 2.7 times more likely to successfully find trajectories enabling navigation from the start to the goal compared to the baseline. The x-axis here is roughly proportional to the number of samples used to build the search graph, and the y-axis is the percent of trials that successfully reach the goal without timing out or failing to find a plan. We see that especially at lower sample counts, our learned sampling distribution enables PRM to find a trajectory. For mutually successful trials, we compare the total distance traveled from start to goal. These plots illustrate the total distance traveled by the baseline versus our approach, where each blue dot is the result of a trial. Using linear regression, we find a robot using our approach also travels a comparable distance or up to 16% less as compared to the baseline, depending on the task and test conditions, even while being significantly more sample efficient. Finally, we tested on a ground robot navigating in an office building. We show the raw sensor measurements as well as a post-process onboard map with a distribution. Our approach, which was trained on simulation data only, extends to real-world navigation. The learned sampling distribution enables the robot to plan down the hallway rather than naively trying to cut the corner. And with that, I'll conclude our talk. We'd like to thank our sponsor and look forward to more discussion in the Slack.